Okay, in this tutorial we're going to be looking at complex numbers in polar form. So polar form is just another way of representing complex numbers. Okay, it has two parts. The modulus, okay, which is denoted by our modular signs as z, which simply equals the square root of x squared plus y squared, where z equals x plus yi. Okay, it's also written as r instead of the modulus of z. As in our modular signs, we can also use it as r, and that will come into it a little bit later on. Okay, and we also have the argument of z, or argz, and that's the angle between the positive real axis and the line joining the origin to z. So we've got a little diagram here. Okay, so if we've got our axes here, okay, so we've got our real part down here, and we've got our imaginary part up here. That should be z, not x. Okay, and this is our point z. Okay, well, if we were to draw a line between the origin and z, the length of that line is the modulus of z, or r. Okay, down the bottom here, that's x, up here is y. Okay, and the angle in here, okay, is our argument of z, okay, or our argz. Okay, and our argument of z is usually measured in radians. It can be in degrees. Okay, now we have problems with just using argz, and that's because if we add multiples of 2 pi, then what happens is we always just get back to where we started with. So it makes it a little bit awkward. So what we use is what we call the principal angle, which is capital A for argz. Okay, and this is the angle between negative pi and pi. Okay, so positive angles are measured this way, negative angles are measured that way. Okay, we just do that so that we don't have this doubling up. So often we talk about the arg with capital A so that we don't have to worry about that doubling up, and that's called our principal angle. Now, since r equals the square root of x squared plus y squared, okay, then our x part here, okay, can be given by r cos of theta. Okay, and that's our angle theta in there, and y is given by r sine of theta. Okay. Also, we find that that theta, okay, is equal to the argument of z, okay, capital A, we have principal angle, and that's found by doing the inverse tan of y over x. Okay, so this means then, all up, that z equals x plus yi can be written as, well, we know that x is equal to r cos theta, so we put that in, okay, and y is given by r sine theta, so we get I r sine theta. Okay, we can simply take out the r as a common factor and get r outside of cos theta plus I sine theta. But mathematicians, what they do is they simplify that a bit further and go, well, let's say that z is equal to r cis theta. Okay, so cis theta. Okay, and that's just for shorthand, so it's a bit quicker to write out than all of this. Okay, so we need to be able to convert between rectangular form, our other form, to our polar form. Okay, so we're going to look at doing a couple of these. Okay, so the first one we're going to do is converting 1 plus I. Okay, then we're going to look at doing minus 4, take 4i. And the last one we're going to look at is just converting minus 5. Okay, so have a look at those ones. Okay, so what we really want to do is we want to start by actually drawing ourselves a picture. So we'll start with A, we'll draw a little picture here to actually represent where this is. Okay, so this is our real component of Z, this is our imaginary component, sorry, I m of Z. Okay, we'll give ourselves a little scale. Okay, but the main thing is that we're 1 plus I. So here at 1 and 1. Okay, so our point's going to be up there. Okay, so when we look at that, when we go, what would be our argument of z? Our r, well, remember that's x squared plus y squared. Okay, well, our x value is 1, so we're 1 squared plus our y value is 1. So that's 1 squared, so we're going to be square root 2. Okay, so r is going to be square root 2. Right, now we need to go, well, what's our angle going to be? Well, we should be able to see pretty easily here without really doing any work, that what we've got is a angle in here of 45 degrees, or pi on 4. Okay, simply because we're going across as much as we're going up. Now, our proper way of doing that, of course, would be saying that our arg of z is equal to the inverse tan of y over x. And when we do the inverse tan of 1 over 1, okay, what we get is pi on 4. Okay, which you could see anyway. So that, putting it together, okay, then we get z equals, remember it's r cis theta. Okay, subbing what we know, r is root 2, cis of pi on 4. Okay, and that's our answer. So we'll have a look at B this time. So again, what we're going to do is draw ourselves a little picture. Okay. So this time we're at -4. Okay, and -4 again. Okay, remember this is our real of z again, and this is our imaginary part of z. Okay, and so our point is going to lie down here. So if we join them up like so. Okay, so what we need to start off with is our r. So our r is again square root of x squared plus y squared. Okay, our x and our y are both -4 in this case. Okay, which means we're going to be the square root of 32. Okay, which is 4 root 2. Okay, so that's our r value, is 4 root 2. Now we need to work out our angle, but where is our angle? Now remember, it's measured from our positive real axis. Okay, and we don't want to go all the way around here, because remember we want to find out what our arg of z is. And remember, that's between negative pi and positive pi. Okay, so we can't go this way because we go past pi, so we've actually got to come this way. Okay, we've got to come that way. So you should be able to see here, okay, again, that, well, we need to know where we're at, so we're in the third quadrant here. If we do our inverse tan of -4 on -4, okay, well, again, that's going to be inverse tan of 1, which we know is pi on 4. Okay, but that doesn't help us a lot, because that pi on 4 is only this angle in here. Okay, it's only that angle, not the whole thing. So we need to add pi on 2 to it as well. Okay, so all up our argument of z is going to be 3 pi on 4. Okay, but of course we've measured in the negative direction, so it's going to be -3 pi on 4. Bring it all together. Okay, again, because we know z is r cis theta, and then say z equals, well, r was 4 root 2 cis of -3 pi on 4. Okay, so I'll just fit in the last example down here, which is -5. Okay, so for this one, again we need a little diagram. Okay. Okay, so we're 1, 2, 3, 4, 5, we're going to be over here. Okay, so our point lies there. Okay, our point lies there. So for our r value, okay, we'll do it the long way, but it should be pretty obvious where our r value is going to be, because we're x squared plus y squared, so we're -5 squared plus 0 squared. Okay, so it's the square root of 25, or it's just 5. Because remember, it's just the distance from the origin to our point, so we can clearly see that's 5. Now, our angle, though, is interesting. Okay, because which way do we go? And I didn't write it down correctly up here. Because we need less than or equals to for pi. Okay, so because we're right on our axis here, well, the question would be, do we measure it this way or this way? Well, we've got to measure it this way because it's pi that's included. Okay, so if we come this way, we get everything from 0 down to negative pi, but we don't include negative pi, so we're going to include it this way. Okay, so our arc of z is going to equal negative pi for this one. Okay, so to finish it off, we get z equals 5 cis, sorry, I'll put negative pi there, cis of positive pi, not negative pi. Okay, so we'll flip over. The next thing we need to look at is going from polar form, okay, to rectangle form, or rectangular form. Okay, so the thing here to remember is really, what does this mean? Okay, well, remember it's actually cos theta plus I sine theta. Okay, so remember that, and don't forget also that x equals our r cos theta and y equals our r sine theta. Okay, so we're going to look at a couple of worked examples here. So the first one is we need to convert 8 cis of negative pi on 6. Okay, that's the first thing that we need to do. Okay, so what we're going to do is going to expand this out into this form here. Okay, so that means that we can write this as 8 cos of negative pi on 6, okay, plus I8 sine of negative pi on 6. Okay, that's what we've got so far. Okay, and you can leave this 8 out the front if you like. Okay, so you could have left the 8 out the front. Okay, but it won't matter too much. Okay, so you need to go, well, what is cos of negative pi on 6? Okay, and from our exact values, okay, should realise that that becomes 8 times by root 3 on 2. Okay, take away, okay, because sine of negative pi on 6 is a negative answer. Take away I times by a half, and sorry, we should have our times by 8 as well. Okay, so it's sine of pi on 6 is a half. Okay, so again, this is where it can be a bit easier to leave our 8 out the front. So I'll take it out, root 3 on 2, take I times a half. Okay, which gives us our 4 root 3 take 4i. Okay, and we're in our rectangle form. Okay, so we're going to look at one more of these type of ones, okay, which is converting 16 cis of 2 pi on 3. Okay, so remember this is going to be written as, okay, it's going to be the same as 16, I might leave it at the front this time, cos of 2 pi on 3 plus I sine of 2 pi on 3. Okay, now cos of 2 pi on 3 from our exact values we get is negative a half, okay, plus I sine of 2 pi on 3 is root 3 on 2. Okay, so bringing in our 16 we get negative 8 plus 8 root 3 I. Okay, we've converted it. Alright, so the next thing that we need to look at, okay, is the conjugates in polar form. Okay, conjugates in polar form. So conjugates are written the same way. Okay, remembering that if z, remember we had if z is x plus yi, then z bar is the conjugate and it's x take yi. Okay, so we still use the z bar notation. Okay, the only difference is that if z is r cis theta, then z bar equals r cis negative theta. And showing that graphically, okay, this would be our z up here. Okay, this would be our z bar down there, because this is theta and this down here is negative theta. It's just measured in the opposite direction. Okay, so we're getting through this section. There's still a bit to go, unfortunately. So the multiplicative inverses in polar form. So basically we're saying, well, what is z to the power of negative 1? Okay, well, we know that would be equal to 1 over z. Okay, and we know that would be 1 over x plus yi. Okay, so if we multiply that by our x take yi over our x take yi, like we've done earlier, okay, then we get x take yi over x squared plus y squared, okay, which basically, this one equals 1 over r cis of negative theta. Okay, so that is what z to the negative 1 to the power of negative 1 equals. It's 1 over cis of negative theta. Okay, so we'll do a worked example utilising this. So we're saying if u equals 2 cis of negative pi on 6, okay, then we want to find the inverse of the conjugate. Okay, inverse of the conjugate. So remember, all we're going to do to find our conjugate, okay, is times this by negative 1. So u bar equals 2 cis of positive pi on 6 now. Okay, then u bar to the negative 1, well, that equals our 1 on r, which is 1 on 2, okay, cis of our negative angle that we just found, so it's back to negative pi on 6. Okay, and what we want, okay, so that's in polar form. They do ask to make it into our rectangular form. Okay, so we need to go, well, this is equal to a half outside of cos of negative pi on 6, okay, plus I sine of negative pi on 6. Okay, from our exact values. Okay, well, we need to actually remember, sorry, a couple of things. Okay, that cos of a negative angle is the same as cos of a positive angle. Okay, and sine of a negative angle is the same as negative sine of that same angle, which we've seen previously. Okay, for our work on trig, okay, so sine of a negative angle is the same as negative sine of that angle, where cos of a negative is the same as just cos of the positive. Okay, so you also get then that cos of pi on 6 is equal to root 3 on 2. Okay, take away I, sine of pi on 6 is a half. Okay, which means in rectangular form we get root 3 on 4, take I on 4, or a better way to write that is root 3 on 4, take a quarter I. It's better to write like that, just simply so that we've got our coefficient of I clearly given. Okay, next part. So, operations in polar form. You do not add or subtract, okay, in polar form. It doesn't work. There isn't any nice way to do it. So if you're going to have to, if you're given complex numbers in polar form and you're asked to add them or subtract them, you've got to change them first to our rectangular form. Okay, we can multiply and divide though. Okay, we can multiply and divide. So if we have Z1, okay, given by R1 cis theta 1 and Z2 equals R2 cis theta 2. Okay, then what that means is that Z1 times Z2, okay, that's given by R1 times R2 cis of theta 1 plus theta 2. Okay, and if we're going to divide, okay, then Z1 divided by Z2, okay, is given by R1 divided by R2 cis of theta 1 minus theta 2. Okay, so remember, if we're multiplying, we multiply our r's, add our thetas. If we're dividing, we divide our r's, subtract our thetas. Okay? So there is a bit of a graphical in the book, but I won't worry about that. Okay, we'll have a look at one direct example for this. Okay, we're given u equals 8 cis of negative pi on 4 and v equals a half cis of 3 pi on 4. Okay, and we're asked to find, you guessed it, uv. Okay, so what we can do is we can use this formula here. Okay, so basically we're going to our r's multiplied together. It's going to be 8 times a half cis of negative pi on 4 plus 3 pi on 4. Okay, so that's going to give us, okay, our value of 4 cis of pi on 2. Okay, and we're done. Okay, the next one is u divided by v. So again, we're just going to use this. So we go R1 is 8 divided by a half cis of negative pi on 4, take 3 pi on 4. So that's going to be 16 cis of negative pi. And that's our answer. So if we keep going, okay, still a bit more to go. Powers in polar form. Okay, if we have z equals cis theta, okay, then z squared, okay, equals r squared cis of 2 theta. Okay, and that basically comes back from what we did just a minute ago, because it means we go r times r, which gives us our r squared, sorry, and we go theta plus theta, which is 2 theta. Okay, if we went z cubed, we can think it's this times this, so it's our r squared times our r, gives us r cubed cis, and it's 2 theta plus theta will give us 3 theta. Okay, you can see where we're going here. We have a nice pattern, which is z to the n equals r to the n cis of 3, z to the n equals r to the n cis of n theta. Okay, that's a nice little rule, and that is called de Moivre's theorem. Okay, de Moivre was a French mathematician around the time of Newton and that mob. Okay, and he came up with this theory here, which works for us nicely. Okay, so we're going to keep going on. Okay, so the next section, which I think is the last one, it is pretty much, okay, is using our trigonometric compound angle formulas. Okay, so we talked about our compound angle formulas in previous videos. Okay, and basically what we're doing is using those, okay, and we're going to show that tan of pi on 12 is equal to 2 take root 3. Okay, we've got to show you that. Okay, so we need to rewrite our pi on 12, because remember our pi on 12 we don't like. Okay, we don't have nice things for pi on 12, so what we do instead is we say that we've got tan of pi on 4 minus pi on 6. Okay, which works nicely for us. Okay, so then what we do, okay, is we go, okay, well let's say that A equals our pi on 4 and our B equals pi on 6. Okay, then tan of pi on 4 take pi on 6. Okay, well that's given to us by tan of pi on 4 minus tan of pi on 6 over 1 plus tan of pi on 4 times tan of pi on 6. And this formula is one of our formulas, our double angle formulas that we've used in the past. Sorry, compound angle formulas that we've used in the past. Okay, so remember tan of pi on 4 is equal to 1, and tan of pi on 6 is equal to root 3 on 3. Okay, so put those values in here. Okay, so this becomes tan of pi on 4 is 1, take away root 3 on 3, all over 1 plus 1 times root 3 on 3, so it gives us 1 take root 3 on 3 over 1 plus root 3 on 3. Okay, not overly nice, okay, but what we can do is we can simplify this to a certain extent. Okay, so what I'm going to do is I'm going to come up here. Okay, so this here, what we're going to do is we're going to put it over the same denominator. So basically what we want to do here is times this by 3 to make it 3 minus root 3 on 3. We're going to do the same thing to our other one and go 3 plus root 3 on 3. Okay, so we're getting there. Okay, sorry, just checking where I'm up to. Okay, yeah, so we flip and multiply. So when we flip and multiply these, because remember we've got this divided by that, okay, if we flip them, okay, we're going to get 3 take root 3 on 3 times by 3 on 3 plus root 3. So our 3's cancel out. Okay, so this is going to give us 3 minus root 3 on 3 plus root 3. Okay. Okay, to rationalize the denominator, that's what they want us to do. What we've got to do is multiply this by 3 plus root 3 over 3 plus root 3. Okay, because it's going to get rid of our thirds on the bottom line. Okay, so that's going to give us 9 minus 6 root 3 plus 3 over 9 take 3. Okay, and this gives us, if we keep going, okay, we get 12 take 6 root 3 over 6. We can simplify further. So we take 6 out of here and go 6 outside of 2 take root 3 on 6. 6 is cancelled out. We come finally down to 2 take root 3, which is what we're after to start off with. So we used our compound angle formula. Okay, that's just what we've done here. Compound angle formula gives us that. Okay, we know that tan of pi on 4 is 1. No, tan of pi on 6 is root 3 on 3. Okay, sub them in. Okay, then basically we're using our knowledge of fractions. Okay, flip and multiply, rationalize the denominator, and simplify all the way down. Okay, So that's basically everything that we've got in this section. So I know it was quite a long tutorial, this one, and again, we're covering a lot of information, and that seems to be the flavour of the month in the new textbook, that we're going to be covering a lot in each section. So again, if you need to, look, just rewatch the video as you're doing some questions and while you're making some notes.